NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Pack the house tonight. Thanks for coming out in December. This is cool. All right, shall we? The InSight mission to Mars, the 12th in NASA's Discovery program, will launch in March of 2016, landing 6 months later in Elysium Planitia. Unlike previous missions to Mars, InSight aims to explore the interior of the planet down to its very core, investigating the fundamental processes of terrestrial planet formation and evolution by performing the first comprehensive surface-based geophysical measurements on Mars. InSight will pursue these goals using seismology, precision tracking, and heat flow measurements. Tonight's lecture will discuss the mission goals and the challenges faced when trying to study these planetary phenomena from a single location. Tonight's guest is a planetary geophysicist, working in the Earth and Space Sciences Division at JPL since 1977. His research focuses on the geological history of the planet Mars and geophysical investigations of the interiors of terrestrial planets. He has participated in several planetary flight instrument teams, including the Mars Orbiter laser altimeters on Mars Observer and Mars Global Surveyor, the synthetic aperture radar on Magellan's mission to Venus, the seismometer on the Netlander mission to Mars, sadly canceled 2 years before launch, and the Sesame acoustic sounder on the European Rosetta Comet mission. In addition, he served as project scientist for the Spirit and Opportunity rovers for 6 years. He helped develop a broadband, space-qualified seismometer, and he's been working for the past 25 years to send seismometers to other planets, particularly Mars. He holds a BS in physics and a PhD in geophysics from the University of Southern California, has served on many NASA and National Academy of Sciences advisory panels, and has published over 60 journal articles, reports, and book chapters. Currently, he is the principal investigator of the InSight Discovery mission. With this launch coming up soon, we're really glad he could make some time for us tonight. So please help me welcome tonight's guest, Dr. Bruce Banerdt.
Okay, well, thank you, Mark. So I'm here today to tell you about the InSight mission. Let's see. So one thing I want to say right up front is that this is a very international collaboration. This mission has a payload which is being built all over the world. These are some of the logos of the institutions. We've got logos from the United States, Germany, France, Switzerland, United Kingdom, Poland, Spain. We've got pieces coming from all over the world. We've really tried to tap, the best scientific and engineering talent from the entire world to do this mission. And so I'm really proud to be the leader of this mission, and I think we're going to get some really cool results that I'm going to tell you about tonight. So let's start in. So what's the goal of this mission? Is as Mark already alluded, we really want to understand. In a fundamental sense, we'd like to understand the methods by which the terrestrial planets, the rocky planets, form. And those are the inner planets of the solar system: Mercury, Venus, Earth, Mars, the Moon, as well as rocky planets around other stars, exoplanets that we're just starting to investigate. And understanding how those planets began, how they were formed, how they evolved to what they are today, is I think one of the fundamental questions that humans have. It's something that it goes back to just understanding where we came from, both biologically and in terms of the world and the universe that we live in. And so this mission, I think, is going to put in place some of the building blocks or put some of the pieces of the puzzle together to understand that. So how are we going to do this investigation? We're going to use geophysical techniques. In particular, we're going to use seismology, the study of earthquake waves, or Marsquake waves in this case. Precision tracking of the spacecraft, and I'll talk a little bit more about what that means, and measuring the heat flow coming out of the planet. So why do we want to study planetary interiors? And this is mostly what I do, is study planetary interiors. And that's maybe not the most obvious thing to do, but it turns out that planetary interiors are really fundamentally connected to just about everything that we see and everything that we do. The interior of the planet is really a big heat engine. It's an engine that's moving. It's being powered by internal heat, and that heat is come from its earliest formation, and it's being generated by the radioactive decay of things like uranium and thorium in the rocks. And this heat engine is driving all the geology that you see on the surface. It's forming the mountains that you see. It forms the valleys that you see, the canyons. On some sense, even erosion, which is sort of powered by the sun. And the sun's what lifts the water and drives the winds and erodes things down. But those things don't happen unless you have elevation differences. And all the elevation differences on the Earth are driven in some fundamental sense by the heat engine of the interior of the Earth. As well as moving things around on the surface geologically, it's also a source and sink of all the volatiles, the atmosphere that we have around us that we breathe. That's where the oceans came from. They basically came from vapor that comes up in volcanic eruptions and from the spreading that goes on in the middle of the ocean. And so it really provides a lot of the necessary conditions for a planet to become and remain habitable. But for our purposes tonight, the cool thing about the interior is it retains the fingerprints of its initial origin, overprinted somewhat by the stuff that happens afterward. And so we can look at the interior, we can look at the structure, we can look at the processes going on in there, and we can sort of use that as a window back in time, back 4.5 billion years ago, to look at the very earliest processes that put this planet together. So what does a terrestrial planet look like on the inside? Turns out that all the terrestrial planets, and by that I mean the rocky planets, all have the same basic structure. They all have a core at the center, which is made of mostly iron and nickel, the heavy metals. It's surrounded by a mantle of silicate rocks, but these are denser silicate rocks than what you'd pick up on the surface of the planet because they're under a lot of pressure, and so the atoms have arranged themselves into a much denser structure. So there are minerals that we don't usually find on the surface. And then on the very outer part of the planet, we have a crust, which is made up of lighter minerals, lighter rocks that have a little bit different composition than the mantle, and those are the rocks that we interact with on a daily basis. All the planets have the same basic structure, but the relative sizes of those different pieces are different for the different planets. And there's differences, detailed differences in the chemistry. It's mostly the same, but there's a lot of fine differences, and those differences are very important in the sort of the evolutionary paths that the planets can take. So we'd like to understand that process. One could say, if you want to understand how a terrestrial planet is built, we've got a perfectly good terrestrial planet right under our feet. Why not study that one? And we do study that one a lot. But there are some drawbacks to trying to understand the very earliest processes on the Earth. And it turns out that much of the evidence that we'd like to see on the Earth has been sort of scrambled up and erased by the fact that Earth is a very vigorous heat engine, and we have things like plate tectonics, which is recycling the crust on sort of 100 million year time scale. So you actually can't go out and actually pick up a rock anywhere on the Earth that's more than about 3.8 billion years old, and we've got about 600 million years of activity before that. When you go into the mantle and you want to look at the structure of the mantle of the Earth actually convects fairly vigorously. So you have hot rocks rising, cooler rocks sinking, and so whatever structural evidence you would have in the mantle from 4.5 billion years ago has been pretty much just stirred up and erased. So we can find out a lot of things about planets by studying the Earth, but we can't really look back in those first few moments of planet formation. The moon's another place you might go. When we did go to the moon, and we did the same kinds of investigations on the moon that we're talking about doing on Mars. But the problem with the moon is it retains a lot of the earliest structure, because it's been fairly dead for a long time. But it's so small that the processes that we're interested in, which are very sensitive to temperature and pressure, never happened on the moon, because if you go all the way down to the center of the moon, you're really just barely below the crust on the Earth. It has low gravity. You don't have that many rocks on top of you when you get down there. And so the pressure and temperature conditions don't really give us much insight into what goes on inside a larger planet. So Mars, it turns out, is kind of the ideal place to go. It's big enough to have undergone all the different processes that we're interested in, or most of the processes we're interested in. It'll take us down most of the way into through the upper mantle and a little way into the lower mantle in terms of pressure and temperature. But we have evidence from looking at the isotope ratios in Martian meteorites that have come to Earth, by looking at the density of craters on the surface. There's evidence that Mars really hasn't changed much on a gross sense since about maybe 100, 200 million years after it formed. And all the interesting stuff on a planet, all the interesting stuff to me at least, happened in about the first maybe 20 to maybe 100 million years after its formation. That's when you go from being not a planet to a planet, much like we see today. So how do we make a planet? We have a rough idea. We have a pretty good idea of the basic ways that we form a planet. First of all, you have a solar nebula. You have dust that's kind of orbiting around the sun. It's made out of meteoritic material, sort of what we call C1 chondrite is a good sample of the early solar system. And so it starts, these dust particles start to agglomerate together from their gravitational interaction. As it gets a little bit bigger, the pieces get bigger, bigger pieces kind of merge into even bigger pieces. It grows, and the interior starts to heat up, and that heats up from both from the energy of these things banging together. There's kinetic energy that's turned into heat. There's a pressure increases. You get adiabatic heating from the pressure building it up, and you also get it starting to heat up from the radioactive decay of the radioactive elements that make up a small portion of all our rocks. So it starts to heat up, it gets larger, the interior starts to melt, stuff happens, and you end up with a planet. Okay, so that's where InSight comes in. We're going to figure out what that stuff is. And if you think about it, it's actually kind of amazing. You know, you start off with this solar nebula, which is essentially pretty homogeneous. I mean, like I said, you have this kind of carbonaceous chondrite material. You have a little bit of ice grains floating around in it. But basically, it's homogeneous. And then you end up with a planet that's got these three, sort of basic different zones, the crust, mantle, and core of different compositions. And nowhere on this planet, if you walk around the Earth, you pick up rocks and you analyze them, you'll never find a rock that has the same composition as these dust particles that you start out with, unless you happen to pick up a meteorite that just fell down, but that doesn't count. Everything on the Earth has been changed. It's like a caterpillar has gone into this cocoon and come out a butterfly. There are no caterpillar rocks left on the Earth today. It's gone through this process which we call differentiation, and all the rocks have been turned into other rocks. And this process of differentiation is what we want to study. So the way that differentiation works, we actually worked this out using information that we got from the moon. This is called the Lunar Magma Ocean model. And the magma ocean means that you start off with a planet that is mostly or maybe even completely molten from all this heat that was generated during its formation. Okay? And as it cools, some different things happen. For one thing, because of gravity, when you have things that are condensing out of this melt, and the first thing that condenses out is you actually have these atoms of iron and nickel and things like that are floating in this melt, and they start to condense together into droplets. And when they condense, they form these droplets which are about twice as heavy as the material around them. And so the first thing they do is they start to go down to the center. The gravity pulls them down to form this metallic core. As it gets a little bit cooler, what happens is then the silicates start to crystallize. And this is a very complicated physical chemical process of crystallization. So as the melt gets cooler, you have certain minerals which condense at higher temperatures, and so it starts to crystallize out at relatively high temperatures. If they're heavier, and it turns out that the ones that crystallize at the highest temperatures are heavier, they'll tend to sink down to the bottom as well. But what if you have this material convecting? If you have a lot of heat coming out, it's going to be boiling more or less like a cup of coffee as you put it on the oven or on the stove, and it'll tend to mix it up. And so if these crystals are sort of entrained in this convecting system, what happens is as that cools down more, these things will be melted into the mix as the composition of the melt changes. And so the crystals that come out of the melt will change as you take things out. So when these things first start to crystallize out and fall to the bottom, then you'll actually end up with higher concentration of the stuff that's left. You'll take out some things with this, you'll leave some things behind, different things will start to crystallize, and so you'll get a pile of stuff that's piling up here of different compositions, and how that forms depends on whether things are moving around, whether it's still, whether it cools off quickly, whether it cools off slowly. There's lots of things that can happen. And at the very end, you'll end up with generally things that are heavier at the bottom, lighter at the top, and so you have your core, mantle, and crust. But the details of this process, how you put together these things, is very dependent, as I said, on the physics and the chemistry that goes on. So what we'd like to do is understand these processes a little better, and we can do that with some relatively simple measurements. So the ideal thing would be to take a rock submarine and just dive down, take some rocks out, put them in our laboratory, figure out what the planet's made out of, and then you could put it all together. Unfortunately, we're kind of stuck up here on the top, and we can only drill down maybe 10 or 20 kilometers, which doesn't even get us down into the mantle. So we have to get a little bit clever about how we make these measurements. Turns out that the models that we've put together using the physics and chemistry that we've worked out in the laboratory and with high temperature and high pressure experiments, we kind of know what some of the reactions are, some of the chemistry that goes on, but we need to know what the conditions are in the inside of the planet and what we ended up with. And so what we know are some fairly simple things. We know about the crust. We can measure its thickness, how thick that crust is, which tells us basically how much of this stuff is up on the top. This is kind of a scum that's floated up to the top, and the amount of scum that you have there, the scum of the earth, so to speak, the amount of scum depends on how much of this planet was melted to begin with. If the whole thing was melted, you'll have a thicker crust. If part of it was melted, you'll have a thinner crust. And so that gives you one of the constraints right away on the beginning conditions of the planet. Another thing you'd like to know is whether there's any large-scale layering in that crust. In other words, when we had these different crystals forming at different times, were they left alone so they could just kind of stack on top of each other or underneath each other, as the case may be? Or did the whole thing get turned over at some point? Because sometimes what happens is you have heavier stuff being accumulated on the surface first, and then you have lighter things that crystallize out later, and then you have instability here. Those light things would like to get up to the top, and so you can actually have things that turn over, remix, and things like that. So if we can actually measure whether there is different compositions as you go down through this crust, that tells us something. In the mantle, we'd like to know how the mantle's working in terms of its dynamics, in terms of its thermal properties. That's really where the heat engine really works. You kind of push heat out of the core, and you kind of pull it out at the crust, but all the work is really done here in the mantle. So we'd like to know its thermal structure, whether we have a relatively shallow thermal gradients you go through here, whether we have convection going on that pulls heat out very quickly, or whether it's just conducting heat out, which is a much slower process. So we'd like to understand the thermal properties of the mantle, and to some extent we'd like to know about its stratification in terms of whether you have different minerals at the upper parts or relative to the ones deeper down. And so that's what we'd like to know about the mantle. In terms of the core, what we'd really like to know is the size of the core, how much metal is down there, what its composition is, which we can get from its density, and its state, whether it's liquid or solid. And those three parameters actually tell us a whole lot about those earliest processes in the planet, because as those droplets are coming down through the molten planet, they're picking up impurities. So we may have not just metallic iron, we might have things like sulfur, we might have some carbon down there. There's other elements that could go down there which tell us how much of that was picked up as you go down, whether small droplets came down quickly, whether big globs came down slowly, things like that. So it gives us information about the dynamics. But it turns out that's also relevant for another reason, is that if you mix in lighter elements into this metallic core, that changes its melting temperature. It's like, dissolving salt in water. You can change the freezing temperature of water. You can melt ice on the sidewalk by putting salt on it. You can actually cause the core to stay molten at lower temperatures if you mix in some sulfur. And so that has implications for things like the magnetic field. Magnetic field, it turns out, has implications for keeping the atmosphere, as the MAVEN mission is investigating right now around Mars. And so all these things are connected not just to the original evolution of the planet and its formation, they're also connected to the evolution of the planet's habitability. And so all these kind of tie together in the end. So this is actually a fairly easy bunch of things to measure. So we take all these things, we put them into a list, and this is what we call our level 1 requirements. This list of measurements are the ones that I basically signed up to do for NASA. When we put together this mission as a proposal about 5 years ago, we were competing against about 25 or 30 other missions. One of the things you have to do when you put together this proposal is say, these are the things I'm going to measure. These are the scientific questions that those measurements will address. And so these are the things that I promised, crossed my heart as a Boy Scout, that I would measure. And they're the things that I listed on that earlier slide, which are about 7 different measurements here, including the heat flux, which tells us about the thermal properties of the mantle. The rest of these are the structure of the planet, sort of the basic structure of the planet. And then we get some things down here more or less for free by the way we do the measurements. And so these are sort of a basic set of measurements that if we can make these measurements, then the people who have done theoretical calculations of the physics and chemistry of early planetary formation can use them to constrain their models and understand how the planets are put together. Okay, so how are we going to do that? How do you actually look down into a planet? How do you get insight into the depths of a planet? You use geophysics, and the most effective tool we have in geophysics is seismology. So what we have is a seismometer, which is right here. Actually, what you can see here is the wind and thermal shield over the seismometer, but I'll show you a seismometer in a little bit. We have something to measure the heat flow. This is called HPQ. It stands for Heat Flow and Physical Properties Package. And that's going to measure the heat flow, and it does it with a mole, which drills itself down into the planet and measures its temperature. And we do it with our precision tracking, which are these two things here, are medium gain antennas which communicate with the Deep Space Network dishes here on the Earth. And so our payload is basically made up of 3 investigations, only 2 of which are instruments, because the radio system is more or less for free because we use that for communication as well. So we have a very simple payload. We have only 2 instruments. That's how I sold it. Very simple, easy to do. But if you look down a little bit more carefully, we kind of cheated because we actually have a whole bunch of other instruments. And these are instruments that we need on the spacecraft in order to support the seismology. And I'll show you why that is. But what we have here is we have a full-up weather station. We measure the pressure. We have a pressure sensor. It's inside the spacecraft and has an inlet up here which is specially designed to negate the effects of wind, so we can measure the pressure without fluctuations from the wind. We have anemometers, a pair of anemometers here called twins, which measure the wind speed and its direction, and also the air temperature. We've got a radiometer, which is something that looks at the thermal emissions from the surface. From that, we can get the surface temperature, and that's something that we need as a boundary condition for understanding the amount of heat coming out of the planet. We have a magnetometer, which is measuring variations in the magnetic field. These things are all things that affect the seismometer, and so we have to make these kinds of measurements in order to get a good seismic measurement. But it turns out that they are also good for their own science, and we'll be doing science with those. But I'm not going to talk too much about that because it's not towards our main mission goals. We also have a couple of cameras. We have one camera that's up here in the arm, so we can use the arm actually to point it. And it's a medium resolution camera. I would say similar to the navigation cameras on Spirit, Opportunity, and Curiosity, except it's not similar. It's actually identical. We took one of their spares off the shelf, and that's what we're flying, except we put a color filter on it, so it'll be color pictures. And we have another wide-angle camera down here, which is a spare hazard camera from the rovers. And I think that's probably about it. Oh, and we have this robotic arm, which turns out to be really key to making our measurements in the sense that it allows us to deploy our instruments to the ground. So let me talk a little bit about seismometer. A seismometer is a pretty sensitive instrument, and it's basically what it is it's a mass on a spring. So if you have the ground here and you move the ground up and down, you accelerate it up and down like this. If you have a nice soft spring here, this mass will tend to stay still. So you move the ground, the mass stays still, and you measure basically the displacement of this mass with respect to the ground. And that's the basics of a seismometer. And so we have the seismometer directly measures that acceleration, and we can turn that into ground displacement. So the acceleration noise requirement for the seismometer, and the noise is what limits the precision of our measurement, is 10 to the minus 9 meters per second squared per root hertz. And so for oscillatory motion, if you're freshman physics, you can get the displacement from the acceleration from an oscillating spring. And you can go through the arithmetic, and you come out with a displacement which is 2.5 times 10 to the minus 11 meters, which is a pretty small amount, but this is what we're actually measuring. Okay, this is a quantum micrograph of a hydrogen atom. So there's the radius of your hydrogen atom. This is the sensitivity of our seismometer. We're actually measuring displacements of the ground, shaking of the ground, which are on the same scale, actually smaller scale than an atom. And we're doing that in the dirt on a planet that's 40 million kilometers away. And we're doing it reliably, and it sounds like magic, but it's not. It's science. We do that sort of routinely on the Earth, but they usually do it in a temperature-controlled basement in a science building at a university. It's a little bit more challenging to do it in the dirt on Mars, and that's why we have these other instruments. Just to give you another idea of what we're talking about in terms of sensitivity, these are some measurements that we actually made on the assembly floor at Lockheed Martin in Denver, Colorado, where the spacecraft's being built. These are spectra of the seismic noise. So this is shaking at different frequencies. So down here we have very low frequencies, and you go up to higher frequencies here. So this goes all the way down to frequencies that give you oscillations over maybe an hour on up to almost a cycle per second. And so you can think of this as a spectrum. Red is low, blue is high, and so we have some seismic energy that's coming through kind of in this frequency band. And this is time, so we just take these frequency spectra every few minutes for a couple of days here. So this is what the seismogram looks like. This is 5 days of data. And you can actually see this is over a weekend. This is where people come to work on Monday, where they go home, they come to work, they go home. Lots of stuff goes on. People are stomping around and stuff like that. But you have this kind of blue blur through here that's there all the time. And what that is, it's called the ocean microseismic band. This is basically the waves hitting the coast in California, messing up our measurements in Denver. So that's the sensitivity that seismology is capable of on the Earth. And so that's why when there's an earthquake in Japan, say, we can actually measure it here in California. And even better still, we can take those waves that we're measuring with our seismometer and do some mathematical analysis on them and learn about the rocks on the Earth as they move through the Earth to get to us. So our seismometer is a little bit more complicated than a mass on a spring. This is sort of the heart of our seismometer. This is what we call our VBB, which stands for very broad band. That means that it measures oscillations from things that take about 7 or 8 hours to complete, one cycle, all the way up to about 5 to 10 cycles per second, a pretty low frequency hum. This is another seismometer that we're flying. This is our short period seismometer. This sort of overlaps a little bit from about a tenth of a cycle per second all the way up to about 50 cycles per second. Still not anything that you could hear with your ear, but getting closer. So we take 3 of these because we want to measure the ground motion in 3 different directions so that we can figure out exactly how it's going. And we pack them into this sphere, which we then evacuate because any air resistance to these pendulums as they're moving will interfere with our motion. We have to level it, so we have these 3 what we call linear actuators. They're basically feet that are motorized so we can level it up so that we don't have gravity pulling it over one side or the other. These things level it to a degree where you can balance a dime on its edge, and at that point the seismometer itself can kind of level itself well enough. But that's the precision to which we have to be able to level this thing, again, on the dirt, on Mars, with the temperature going up and down by 100 degrees a day. Okay, so Martian seismology is what we're going to use to probe the center of the planet. But in order to do seismology, you have to have signals. Do we know that there are Mars quakes? And the answer is we don't actually know that because we've never measured it. So we could say, well, it's a good idea to go there and measure it. And NASA says, well, for $500 million, you have to give it more than a good idea. You have to be pretty sure it's going to happen. So we did a lot of analysis, a lot of theoretical analysis. And fortunately, we can go to Mars, we can look at it from orbit, and we can see faults on the surface. All these lines that you see on the surface, the wrinkle ridges that you can see in the lava plains, the Graben canyons that you can see, those are all formed by motion along faults, and so we know that there's lots of faults on Mars. Unfortunately, most of those are 3 or 4 billion years old, so that doesn't help us much today, but you can actually look at the age of all those faults, and you can see that there are fewer and fewer faults with time, but you can extrapolate through those, and you come up and you can extrapolate to the present, and you come up with a rate of fault movement, which is in this band right here. And this plot is number of quakes that you expect per year as a function of the size of the quake. In this case, it's seismic moment. Up here, we have sort of equivalent magnitude. So the bigger the quake is, the fewer that you expect to see per year. And so it follows a slope like this. Lots of quakes that are very small, fewer quakes that are very large. And this is the sort of the band that we come up with from that theoretical, based on observations, but an extrapolated estimate. If you look on this plot, this line right here, that's the level of activity we saw on the moon. So we sent seismometers to the moon back in the 70s with Apollo. We measured lots of moonquakes. We had very sensitive seismometer. It was there for about, we had 4 of them there for about 7 years or so. So we got a pretty good level on the moon. Since the moon is relatively inactive, it's down here below. It's at lower numbers, but we can be pretty sure that Mars is going to be more active than that. It's got lots of volcanic activity that's extended through time, much longer than on the moon. In fact, there's evidence for lava flows that are maybe less than 10 million years old, so it's active up to the present. This line up here is the line of activity that you get on the Earth. So this is on the Earth if you take away all the plate boundaries. So you take away the mid-ocean ridges, you take away the trenches, you take away the San Andreas Fault, and all you're left with is Missouri and Canada and Australia, places that are relatively, you would think are pretty dead seismically. We do get earthquakes in the middle of plates, but not very often. And so that's this line. Mars we estimate to be below that line, above the moon line, and so that kind of makes sense that Mars is less active than the Earth, more active than the moon. So this is what we expect to see on Mars from the faults that we can see. And if we get that kind of activity, we have plenty of Mars quakes to use to do our analysis. But if it turns out that we're unlucky, we actually have a couple of guaranteed signal sources that we don't have to worry about. We have the Phobos tide. So this is the moon Phobos. It goes overhead about every 7.5 hours. It's a pretty small moon, but just like the Earth's moon, it does raise a tide. On the Earth, we're familiar with the tide from the ocean, but you may be less familiar with the fact that the ground underneath you actually rises by almost a meter every time the moon goes overhead, and actually when the moon's on the other side of the planet too, because it happens twice a day. So the ground's going up and down underneath you every 12 hours or so. We don't know it because everything goes with it, but we can measure that with sensitive instruments on the Earth. Phobos, it turns out, is smaller, so we only get about a centimeter of displacement. But by measuring that displacement, we can actually tell something about the inside of the planet, because if you have a liquid core, you'll get a little bit more displacement than if you had a solid core. So it's like, trying to squeeze a hollow ball versus squeezing a solid ball. If you have it hollow, it's easier to squeeze. And so by measuring how much, whether it's 1 centimeter or 1.001 centimeters, it's the difference between a liquid core and a solid core, so we can actually figure out whether the core is liquid or solid very quickly. And then if we keep on measuring this day after day after day after day, it turns out we can get a more and more precise measurement of that displacement. We can actually then see how big that core is. So this is one of our methods of actually getting the size and the state of the core for free, right? Another thing we have are meteorite impacts. Okay, so on the left here we have a map of meteorites that have been detected from orbit with the high-resolution cameras on Mars Reconnaissance Orbiter. And so they have before and after pictures. So this is a picture that was taken in June of 2008. This is a picture that was taken about 4 months later. And you see this black spot here, and if you blow this up with a high-rise image, you can actually see a whole cluster of craters here from a meteorite that broke up and hit the surface. So there's lots of these things. These have been measured over about 10 years or so. So there's even a couple in our landing area. So we have meteorites that are hitting Mars all the time. Mars has a thin atmosphere. Turns out you don't really stop much with the Martian atmosphere. And so these things come right in and go bang. When it bangs on the surface, it creates seismic waves, just like an explosion would. And so we can actually use those waves to probe the interior. So again, that's another guaranteed signal source. Another thing that's a little bit more esoteric is atmospheric excitation. So this is a picture of a simulation of the atmospheric pressure. So these are winds that are coming across. Winds are always driven by differences in the pressure. So you have high pressure, the air moves towards low pressure, and it eddies around and does all kinds of stuff like that. So this is about a 5 by 5 kilometer square on Mars. And as these pressure waves go by, they're pushing the ground up and down. And if you take any kind of a object and you start pushing on it, you push on it everywhere, you're basically pushing energy into that object. And if it's a finite object, it wants to vibrate at certain resonant frequencies. So it's like a bell. If you sit there and just kind of just tap on a bell and tap on it and tap on it, you'll start to build up that ring, and you can measure that frequency in the terms of the planet, and those frequencies will tell you something about its structure, its density, and so forth. So this is right about at the limit of our sensitivity, but we think we may be able to use this to probe the planet as well. So we have lots of different ways to probe the planet, and we've got lots of techniques. I mean, one thing people ask me a lot, because if there's one thing people know about seismology, they know that you need 3 stations to figure out where an earthquake is, right? Because you need to be able to triangulate it. I think especially in California, people have a little bit of an idea about how you do seismology. But we're only having 1 station on Mars. How can we actually use that station to do the science if we can't even locate where our Mars quakes are? Well, it turns out there are a lot of techniques for getting around that. I think the one that's going to be our bread and butter is it uses the fact that Mars is a smaller planet, and so we actually get a lot more of the energy from a Marsquake to get to us than you do on the Earth, where it has to go a long ways. And we use the fact that instead of just having a P and an S wave that come, and normally you use P and S waves from 3 different places to figure out where, X and Y and T, the time of the event occurs, we actually have more information because we can use surface waves that go around the outside of the planet, and that gives us another wave arrival with another velocity. But once that hits our station, it keeps on going around the planet again, and we can actually see it coming around the second time. And so in that case, we know exactly how far it's gone. We know how long it took because we have the timing of those two arrivals. So we can use that information and start backing out that along with the surface wave that went around the long way, these body waves, the P and S waves that went straight through the planet. And by using that, we now have 5 pieces of information. We can then put it together to get the location of that event. And once you have the location, you have the timing, you can figure out what the velocity is, and the velocity is what tells you what it's made out of. We can actually take a rock in the laboratory, we can bang it on one side, we can figure out how fast the waves went through, and that speed, that velocity of those waves, those sound waves going through the rock, are different for different compositions. And it turns out that you have a planet acting exactly like a lens acts for optics. So these are waves, they get bent by going through different materials, they get reflected off of boundaries, and we use all that information then to put together the structure of the planet. These other things are actually using different aspects of resonances. Like I was talking about before, you have a planet, you have these things that they want to ring at certain frequencies depending on how big things are, how dense they are, how springy they are, and by using the frequencies, we can then pull out things from the surface waves using their properties. We can pull things out from body waves and the multiple bounces between the top of the crust and the bottom of the crust, and we can use the ringing of the whole planet from the largest quakes to look at these little spectral peaks here at different frequencies. And so we have lots of different methods in seismology for taking a single station and putting together the structure of the planet. So a Marsquake is like a little flashbulb. It goes off and it illuminates the inside of the planet. And we have one little camera sitting over here in one place of the planet, so we have to have a lot of different flashbulbs going off at different places, illuminating different little pieces of it to be able to put together a 3D picture, much the same way that you put, an MRI puts together a 3D picture of the inside of your body when you go to the doctor. Okay, so that's our main instrument is a seismometer, but in order to get the thermal properties of the planet, we'd like to know how much heat is coming out of the planet because that tells us what's powering this planetary engine. The way we do that is with our HP cubed. It has a self-penetrating mole, that's this little torpedo here, that digs its way down up to 5 meters down into the surface. That's 15 feet. That's about the size of this room. So you figure out going down from that, the ceiling to the floor, that's about how deep we're planning to go with this mole. So that's our journey to the center of the planet. We go down that far. That's close enough. But along the cable that connects it, because you have it has to be powered somehow, we have thermal sensors about every 35 centimeters or so. And so we can measure the change in temperature as you go down. So I don't know if you've ever been down in a mine, but it gets warmer and warmer the farther you go down. And that's because you're getting closer and closer to the hot part of the planet. And it's actually that thermal difference, the thermal gradient, that's pushing heat out of the planet. And so in this upper 5 meters or so, we can measure the very fraction of a degree increase in temperature. And by measuring the conductivity of the rocks, along with this temperature increase, we can figure out how much heat comes out, is flowing out of the planet today, and that then can be extrapolated down to the depths and help us to figure out what is actually happening to transport that heat out of the planet. So this is a little video. This shows how it works. Okay, so we have this mole. We have a hammer which pushes the mole forward. Now, if it's just hanging out in space, it would just go back and forth because you have equal and opposite reaction, right? So we have the motor that's running on a little cam up here. It pushes it against the spring bangs it down very quickly, and then it recoils, and we have a spring up here that's softer, which actually takes up some of that recoil. All the force is still there, but it slows it down and allows the friction of the ground on the side of this mole to be more effective. So the faster you try to push something, the less friction you have. So we have it going very quickly down, and then the recoil is actually resisted by the friction of the sides on the sides of the mole, and it bangs its way down into the ground. It sounds like magic, and we had to actually prove to our review panel that this would work, and so we put together a 5-meter high tube of soil in a lab in Bremen, Germany, where they built this, and we showed that this thing bangs right down through there. It takes about an hour and a half to go from the top to the bottom. So that's our heat flow, and then our final experiment is the precision tracking experiment, and this is where we really start getting into magic, because over the last 50 years, the Deep Space Network and the scientists that work with it have developed techniques that use the radio waves that are sent to the spacecraft and then from the spacecraft back to Earth to be able to locate spacecraft at Mars's distance to a precision of about 10 centimeters. Okay, so that's about 4 inches. So we know where our spacecraft are in space with respect to these deep space antennas to an accuracy about 4 inches. Maybe the ones that are flying around, not that good, maybe only 20 or 30 inches. But they've developed this, they can track it. Since we're on the surface of the planet, as you track the spacecraft, you're actually tracking the rotation of the planet. So we track it for about an hour a day, for 4 or 5 days during the week, and we can use that to figure out where the rotation axis is, how fast it's rotating, and what the direction of that rotation axis is pointing. And it turns out the rotation axis of Mars changes over a couple of different time scales. The first time scale is the so-called processional time scale. That's the wobble that you see in a top. So when you spin a top, it spins very quickly, but it wobbles around a little bit more slowly. And it wobbles because gravity is trying to make it tip over. And since it's spinning, instead of tipping over, it pushes it sideways. And so it wobbles around. And the speed of that wobble is determined by how fast the top is spinning, and it depends on what's called a moment of inertia, which is the distribution of mass away from the axis. So it's like a ballerina, an ice skater. Ballerinas spin at one speed. Ice skaters, when they pull their arms in, they are decreasing their moment of inertia, but their energy stays the same, so they spin faster. And so the moment of inertia of the planet tells you where the mass is concentrated, whether it's concentrated close to the center in the core, or whether it's more distributed. So the bigger the core is, the larger the moment of inertia is going to be. And so if we measure this moment of inertia very precisely, that gives us a measure of the size and density of the core. So here we get the moment of inertia from this precession. It wobbles once around that cycle every 165,000 years. So we could just sit on the Earth and take pictures of it with Hubble and wait 165,000 years and measure that very precisely, but we're impatient as scientists. So what we do is we measure the pole at one time. We measured actually which way the pole was pointing during Viking, 1976. We measured it again during Pathfinder, which was 20 years later, in 96. We'll measure another, and we got an estimate of the moment of inertia, but those measurements, because the technology was 50, 40 years older, they're not quite as precise. We can make a much more precise measurement now, use the Viking measurement and the Pathfinder measurement to increase our precision of that moment of inertia to get a better, of the speed of the wobble, to get a better estimate of the moment of inertia. It also wobbles on a faster time scale, which are called nutations. These are wobbles that happen over the course of a year or less. And these are actually from the interaction between the liquid core, which kind of sloshes around inside. It's not quite coupled. It's not solidly coupled to the rest of the planet. So as that sloshes around, it wobbles a little bit. And that's a very small wobble. It's only wobbling by a few meters, but we can measure that with this precision tracking. 2 years of tracking will be able to determine the amplitudes and frequencies of these nutations, and that actually will be able to directly give us the core size and density. So that's our other probe of the core. So a little summary of the mission itself. We're flying a near copy of the successful Phoenix lander. We're using the same spacecraft design with just a few modifications to make it operate better at the equator, which is where we're going instead of the pole. We launch on during the month of March sometime next year from Vandenberg, California. We have a very fast trajectory because we're on a very big rocket with a very small spacecraft. They don't make small rockets that Phoenix launched on anymore, so we actually can get to Mars very quickly. So we launch from Earth and come around here and hit Mars in less than 1/2 of an orbit around the sun. So we land in September, which is about 6 months after our launch. We spend 2 years on Mars, which is 1 Mars year, so we go through a Martian winter and summer cycle. We have very repetitive operations because all we're doing is, listening for seismic waves, sensing the temperature. We don't actually have to do anything active, and our nominal end of mission is in 2018. And of course, the cool thing about this whole thing is Vandenberg. So instead of having to deal with alligators in Florida, we get to play with otters in California. And again, the reason we can do that is because we're launching on a large rocket. Normally, you're trying to squeeze every bit of energy you can out of a launch. And so you get near the equator and you launch in the same direction that the Earth's rotating, so you get a little bit of a slingshot effect. You launch to the east, and that puts you into orbit so that you can go off towards Mars. Since we have a rocket which has more energy than we need, we can actually launch from Vandenberg, California. We launch almost due south, and we kind of go up and around the pole and head off towards Mars. This simplifies a couple of things. First of all, we don't have to take a bunch of plane flights to Florida, which costs a lot of money. But also, it turns out Florida, during the time we need to launch, there's a lot of Atlas launches that need to go off. And so we were actually able to do NASA a favor and sort of take some of the traffic jam off of Kennedy Space Center. So this is what our spacecraft looks like. We've actually completed the spacecraft. We completed it last May or June, and since then we've been doing a lot of testing on it, seeing whether there's any problems, and we found several problems, which is normal when you're putting together a very complex system like this. We've been able to fix them. This is a spacecraft pretty much all buttoned up in its launch configuration. Here we're putting on the back shell, which protects it in space. If you put it all together, it looks like this. So we have a heat shield up here. These are the solar panels it uses on its cruise between Earth and Mars. This would be the rocket. So we have this adapter that helps us attach to the rocket. And this is the way we travel to Mars. Once we get to Mars, we unfold it the way Phoenix did, and this is our glamour shot. They had a professional photographer come in here and pose it and everything. So you can see the solar panels out here. This is the deck where all our instruments are going to live until we get to Mars. And here is a little bit of an animation. So this is InSight cruising through space. We get to Mars, we eject the cruise stage, which has those solar panels on it, and then we start entering the atmosphere. We burn off a lot of the energy using that heat shield, just the same way Apollo did, same way all Mars landers do. We come in very, very quickly and get rid of most of the energy with the heat shield. We get down about 2 times the speed of sound. We pop a parachute, which then brings us down closer to the surface. We eject our heat shield. We deploy our legs, and then we drop off the parachute about 1 kilometer high. We start up our rockets. We come down. There's no airbags. There's no sky crane, no crazy stuff. We land on rockets just the way God intended us to land on a planet, right? So once we're down, safely down, we then have to get ready to actually survive on the surface, and we do that by deploying these our solar panels. This all happens during the first 20 minutes, half an hour that we're on the surface of Mars, and then we're ready to go. You can see the deck here is all crowded up with stuff, and I'll tell you a little bit about that in a few minutes. This is where we're landing. We're landing in the western part of Elysium Planitia. Oddly enough, we're only about 300 kilometers from Curiosity, 300 kilometers north of Curiosity. That just turns out to be the best place for us to land for a bunch of technical reasons. None of which are scientific, because when you're studying the core of the planet, no matter where you land, the core is under your feet, so that's fine. But for technical reasons, this is the safest and easiest place for us to land. This is kind of a crowded side of Mars. We've got Spirit, we've got Curiosity, Viking 2 was here, Beagle 2, Rested Soul was over here. But this is where we'll end up, and these are our ellipses. We're landing in an area about 120 kilometers long by about 25 kilometers wide. So surface deployment is one of the things that we spent a lot of effort figuring out. We actually sent seismometers to Mars once before, back in 1976 on Viking. Each of the Viking spacecraft had a seismometer. So this is a picture. This is actually the seismometer right here, the Viking seismometer. This is the ground. So what's wrong with this picture, right? We're supposed to be measuring, ground motion at atomic levels, and we're sitting up here on a spacecraft that has shock absorbers on it. So, and the reason for this was the seismometer was like the very last thing that they accepted on the payload. It was sort of last in line for all the resources. We didn't have an arm that could pick it up, so we hoped that we'd have some fairly large quakes that didn't materialize. So my genius was to figure out how to put the ground and the surface in the same place. It's not really that hard. And we do that with a robotic arm. So we pick up our seismometer. It's connected to the deck with a bunch of explosive bolts that unlatch. We take it out. We've already mapped out this ground with our camera and done some 3D analysis to figure out what a good, safe place to put the seismometer down. Once we've taken some pictures with our camera, we've done some analysis of our noise level, and we're satisfied with where we are, we go back and pick this thing up. This is our wind and thermal shield. It's a aluminum dome. It's about almost a meter across. You pick it up, and ooh, there's something cool. It's got a skirt. Okay. Nice pleated skirt, like you'd wear at a square dance or something like that. And it's up on legs. And as you put this down, this is thermal protection around here, thermal blanket. And underneath here, it has a chainmail. And this actually makes a very good seal with the ground. Doesn't let the wind in. Makes a nice, snug little cocoon for our seismometer to sit in and be relatively shielded from the environment. And once we finish with that, we go back and do our last deployment, because if we actually started the mole here, it would go right down through our computer, and that wouldn't be good. So we want to put it on the ground as well. Each of these things is, of course, connected back to the spacecraft by a cable that allows us to power it and get our signals back. So we put the surface structure for the mole on here. The mole actually lives in this little chimney here. Once we put it down on the ground, we let go of it with our arm, and then we can release the mole, and it starts digging its way down to its 15-meter depth. So we would like to leave you with this picture. This is a picture that Spirit took back in 2004, I think. It's an image from Gusev Crater. This is the rim of Gusev Crater. This little dot up here is the Earth. And so I think this picture is very emblematic of sort of our mission goal, which is to get insight into the Earth by exploring Mars. And with that, I'll take some questions. And if you want to ask a question, could you get up and go to the microphone, because that way people will be able to hear you.
Bruce, and how do you measure the thermal conductivity at about 5-meter depth? Otherwise, if you don't, it's just a thermal gradient.
Right. We actually measure the thermal. We have heaters on the mole. We stop about every half meter, and we put a heat pulse in. Then we turn off the heater. We look at the decrease in temperature, and by looking at how quickly the temperature goes away, you can get the thermal diffusivity out of that. Yeah. Yeah, and that decays away, and after a few weeks, that's no longer contaminating our temperature measurement. Sure. Yeah.
In regard to the meteorite, ALH 84001, Are there any current meteorites that have been discovered that are like that?
Well, Allen Hill's 84001 is one of a whole collection of meteorites that we've gotten that have come from Mars. That one's famous because of the various different structures that they found in it that have been interpreted in terms of the result of biological activity. And there's a lot of controversy over whether it's actually biological or not. But we do have lots, dozens of meteorites that we can identify as having come from Mars. Just they were blasted off by a big impact on Mars, and they flew through space for a while and eventually ran into the Earth. And we can use those for lots of things. Most relevant to us is they can actually look at the amount of radioactive material in it and do some age dating of these things. They can look at the detailed mineralogy of these meteorites and determine they came from the mantle of Mars. So we know something about the composition of the upper mantle of Mars, at least, that we can use to constrain our models. And so those are very useful that way.
Thank you.
Sure.
Good evening. Assuming that the mole encounters a really hard boulder, maybe 1 meter down instead of 5, how will that affect your science?
Okay. Yeah, we actually thought about that a little bit because obviously, one thing you don't want is for the mole to go down and go, bonk against a big rock. And there's a couple of things that we've done. First of all, we picked our landing site pretty carefully. It's a Hesperian age, which means it's about 3 billion year old surface, which means this has been sort of pulverized by meteorites for a long time. And there are some large craters sort of around the edge of our landing ellipse where you can look at a cross section of the material underneath. And we can actually show that the density of rocks is, if you convert it into a surface coverage, it's about 4 or 5%. And you can do the statistics, and statistically, we've got about somewhere between 92 and 98% probability of getting down to 5 meters without encountering a rock. So, but if you're not lucky, there's a couple of other things in our favor. First of all, small rocks, anything up to about a couple inches, it'll actually just push out of the way. It's pretty strong. And if it hits a bigger rock, if it hits it flat on, then that's it. That's as far as we go. If it hits it at an angle, if you're on the edge of a rock at about roughly 45 degrees, it'll actually dig a little gouge, turn around, and actually keep on going at an angle. We have tilt meters inside the mole that actually measure the angle that the mole is going. So if it doesn't go straight down, if it goes down at an angle, we can then still figure out what the depth is that it gets to. We can figure out what the depth of all the different temperature sensors are and correct for the vertical gradient. So it'll go around some rocks if it hits them enough at the edge. And if we only get down to, we have to get the tip of the mole down to about 2 meters in order to be able to make our measurement. If we get it down to 2 meters and we last for a year, we can pull out our measurement at the precision that we need. So 2 meters is kind of like we'll be keeping our fingers crossed till we get to 2 meters, and then it's kind of like everything after that's gravy. So
Thank you.
sure.
Well, my question is kind of the opposite of the last one. This seismometer, since you're putting it just on top of the ground, what are the effects of it sitting on loose dirt rather than being anchored to like bedrock?
It's actually a pretty effective coupling. I mean, you do worry about the coupling between your surface and the seismometer. Normally, what we do on the Earth is they put them on cement piers, and they just have little pointy feet. They don't bolt them onto the cement. They actually just set them on there, because if you bolt it down, it turns out just the stresses in there, they keep on kind of moving around to the levels that we're talking about. So they just have points sitting on the cement. But you can measure it on the ground. There's some microphysics that with the way the grains kind of rearrange themselves. They do on the Earth, they do seismology in the field, and there are ways of dealing with that. We've designed the feet with a cone with a flange that actually gives us pretty good coupling. And the seismic waves, it's not like we're vibrating so fast that you can't follow the ground. The fastest oscillations that we're looking at are relatively slow, and our bread and butter is in the kind of the 1 cycle per second and slower regime. And so it's not like I said, you're not going to be like scooting around on the ground at those levels. The more difficult problem is actually if you have dirt, you tend to get noise that gets trapped in this dirt. Dirt has a low velocity, and you trap it between the bedrock below and the surface. And so that kind of increases the amount of noise that you tend to get. But we've done calculations of the level of sort of extra noise that we get from that, and we're okay with that.
Thanks. And just quickly, do you expect for the initial period of time the feet will settle in?
Yeah. For the first month or so, we'll probably have some issues with settling.
Thanks.
Sure.
Hello, Bruce. I really enjoyed the presentation. Thank you. Something that was missing was there was no talk about how the atmosphere, the situation of the atmosphere of Mars affects these data. Is it truly not affected by what the conditions of the atmosphere is?
Oh, it's very much affected. That's why we have that shield over it. And that shield, I mean, it looks like we just bought a wok and turned it over and put something. But there's a little bit more to it than that. We actually did a lot of hydrodynamical calculations, and that dome is actually aerodynamically formed so that it actually has negative lift. So when the wind blows, instead of just flipping up and rolling away like a tumbleweed, it actually presses down and stays in place. And like I said, we designed that skirt to kind of seal around the bottom so that we don't have the wind going directly against the seismometer. But it still has friction on the ground, is blowing the spacecraft. It blows our solar panels. But that we put on our anemometers, those 2 wind sensors, so that we can measure the wind. And what we do is when it's very windy, we just kind of throw that data away because it gets too noisy. But we need to know when the wind's blowing and when it's not blowing. One of the problems with Viking is that it had an anemometer as well, but since they were limited in the amount of data, usually they turned on the anemometer and turned off the seismometer and vice versa. So when you did get a signal on the seismometer, you're going, oh, I think that actually is probably wind, but you didn't know for sure. So we're running at the same time. So the wind is one problem. Turns out the bigger problem is not the wind, it's actually pressure variations. And it's not because the pressure pushes on the seismometer, it's because it actually, if you get like a little breeze going by, just kind of, 3 or 4 miles an hour, very, very mild, it changes the pressure by, a fraction of a thousandth of an atmosphere, and it pushes down on the ground just a little bit harder or a little bit less, and it tilts it, and the seismometer go, whoa, this is a big. So we actually have a very, very sensitive measure of the pressure, not just the static pressure, but the pressure variations in our frequency range. And so by doing that, we can actually, measure the pressure. We can look at the signals on the seismic record, and mathematically we can just eliminate those signals out to get our data back.
So when you showed me when you showed us the pressure that can apply from the atmosphere of Mars, and you can potentially look at it with your seismometer. I'm not going to get too excited in here, but with all this methane on Mars, and can we potentially figure out what the mixing gas ratios are in the atmosphere of the Mars?
Not from our measurements. We don't have any compositional measurements at all.
But we can see how the mixing and the pressure is near the ground.
Yeah. We can look at pressure variations. We can look at the wind speeds. On an earlier proposal, we actually had measurements of the wind at three different elevations, so we could look at boundary layer processes and really do some really interesting meteorology. But in order to get we had a a cost cap that we had to stay underneath, and so I had to kind of ruthlessly chop off all the other really cool instruments that we were going to fly in order to do that. But other missions are planned to look at that, so.
Well, thank you.
Sure.
So my question isn't really about InSight, more about Mars in general. Obviously, Elon Musk has been generating a lot of controversy, I guess, or a lot of debate between his...
I like to call it interest.
Yeah, his interest in Mars. And the most recent one, I think it was like reported in September, he wants to quote unquote nuke Mars. I just wanted to know what your opinion on that was.
Yeah, I don't remember reading that one, but that would be great for us because one of the other things that we've looked at in various other mission concept is actually taking our own seismic energy to Mars in the form of basically cannonballs. So we put our seismometer down, and then you just kind of come in, from space and have your own meteorite and have it hit, not on the spacecraft, but maybe 10 or 20 kilometers away, and that'll generate enough seismic energy that'll go down, bounce off the bottom of the crust, and come back up again. So you can actually take about 5 kilograms of tungsten, because tungsten doesn't burn up very much, and if it comes in at the speed that you come from the Earth, like I said, you can actually probe the crust with these things. And get some pretty good data. If you get something bigger, gets 100 kilograms or stuff, or something, you can get it farther away and get more penetration. So, a nuke, that would be a great seismic source.
And if he doesn't go with that plan of nuking Mars, do you think he can possibly maybe even work with NASA to get civilization or himself onto Mars?
I wouldn't put it out of the realm of possibility. I mean, one of the things that NASA is always being pushed to do by Congress and who are funded by taxpayers is to collaborate with private industry to both bring down the cost of space exploration and to bring in more expertise. And so I would say that that's certainly a possibility. The things that are happening in terms of sending humans to Mars, NASA has a big program that's aiming at sending humans to Mars maybe in 20 years or something like that. And that's all very interesting, but I'm not really an expert in that, so.
Thank you.
Sure.
You mentioned that Mars might have quakes like the ones we have in Missouri on the New Madrid Fault. At this point in time, do we have any idea how strong Mars quakes might be using the kinds of measurements we use to measure earthquakes here?
We've measured, we've made some calculations. We can only guess, and they're all pretty much just statistics. Earthquakes are a stochastic process. You get a lot of small ones, you get big ones, and kind of an average time between them, but it's random. You can get 2 big ones really close together, or you can have a long time in between. And so we have a calculation of kind of the largest Mars quake that it looks like it's reasonable to support on the kinds of faults that we see. There's actually an interesting paper about 2 years ago where a photogeologist looked at boulder tracks where boulders had actually rolled down a very long ridge. And all these boulder tracks were very recent. They were tracks in the dust at the surface, and they would disappear in maybe a few thousand years just from the wind action. And he found an interesting pattern where there was a lot of boulders that had come down in this one area, and then it died off as you go farther each direction down the ridge, and he matched it to a similar pattern that was seen in Italy with an earthquake. And it just shakes boulders loose, and then they roll down the hill and leave these tracks. And by looking at the length of this area that had boulders coming down, he actually calculated the size of a Mars quake that would have been necessary near the center of this thing to make that happen. And he came up with something that was like a magnitude 7+, so a pretty good sized Mars quake. We've been sort of conservatively saying magnitude 6-ish is the largest that we would expect to see. And even that, we probably only see 1 or 2 of those every couple of years, which means we might see one or we might not in our 1 year. Of course, the length of time that we're planning to stay there, a Mars year, is not an accident, because it turns out that if you design a spacecraft to survive a Martian summer and a Martian winter, there's no real good reason why it can't survive another Martian summer and another Martian winter. And so I have a hope that we can actually last for much more than our prime mission of 2 years on Mars, that we'd be able to sort of build up our statistics on the Mars seismology over several years. And the longer you stay there, the more likely you are to see one of the larger quakes that are going to be more rare.
Thank you.
Sure.
Okay, you took most of my question because I wanted to know how long you thought you might last there. But if you did last longer, several years, and you explained how you can do so much with only one seismometer. But I would imagine if you had more than one seismometer, that would be nice.
Yeah.
And wouldn't it be fairly easy to add a seismometer to another mission? That wasn't just, it was just landing anyway. You just drop this off and
that's exactly what I tell NASA. Just put it on there and drop it off. But it's a little bit more complicated than that. We definitely have advocated that. I've actually been advocating now for a seismometer on Mars for more than 25 years. And since this is the first one that's gone since Viking, you can see how successful I've been. But there have been several times where we came close, and we have advocated, me and my friends, we have advocated that you should go with this, every time you go to the surface, you should take down a certain sort of standard instrument. You should take a weather station, you should take a seismometer anytime you go down. But you have to be able to support it, and the seismometer, the big problem with the seismometer, it doesn't take much power, it's not very heavy, it doesn't have to be very heavy. The big problem with the seismometer is it generates a lot of data. We're taking about several hundred measurements a second continuously, and that adds up to a lot of data. In fact, we only bring back about maybe 3 or 4%, maybe 5% of the data that we collect with our link to Earth, and we have some fairly sophisticated ways of figuring out which data is important. Most of the time, we're just measuring wind and noise and stuff, and we have a way that we can actually just bring down the pieces that are interesting to us. So whenever you put a seismometer down, you have to have a radio on it that can get all that data back, and radios take power, and they have to be kept cool, and that requires thermal systems. And pretty soon you end up having a little bit more than you'd like, which has always been the problem in the past. But I agree. We have people whispering into the ear of the project manager on Mars 2020. Just drop off the seismometer. It's probably not going to happen, but we'll keep on working on it. And the Europeans have some ideas about that as well. So we could actually get a companion seismometer to keep us company on Mars sometime in the near future.
Thank you.
Sure.
If you don't deploy your mole too quickly after you deploy the seismometer, couldn't you use the vibrations from the mole to help calibrate the seismometer?
We can use the vibrations from the mole not to calibrate the seismometer, because it has its own internal calibration, which is more precise. But what we can use it for is actually we can do seismology on a small scale. So we have this mole that's going bang, it's putting waves through the ground. In particular, if it goes down and hits bedrock, those waves will bounce off again. And so, you have waves that come straight to you, you have waves that can bounce off of layers, and it's not optimally set up to do that, because most of the frequencies coming from the mole are going to be high frequencies, and we only go up to about 50 cycles per second. But this is actually so fun that most of the people on our team are actually, kind of in their spare time trying to figure out how to use this mole information. They figured out how to, interpolate and get, basically double the effective frequency and get better resolution. And so, I think that one of the first papers that might come out of this seismometer is actually analyzing the mole penetration data to get the shallow structure, the upper, tens of meters of structure underneath our spacecraft, which isn't part of our main goal, but that doesn't stop it from being cool science.
Right. Thank you.
Sure. Now, did we get any? I think we have a chat going on, and we're getting some questions from the internets. So, Kaylee's Taxi says, what were the challenges in developing these instruments for Mars versus Earth, i.e. landing, robotic deployment, environmental conditions? Okay, so the biggest challenges for developing instruments to go to Mars are getting them so that they work in the Mars environment. So on Mars, during the day, the temperature goes up and down by 40 or 60 degrees centigrade, and you almost double that to get Fahrenheit. And then you have another 40 or 50 degrees from winter to summer. And so being able to operate over that huge temperature range, it's like going from Death Valley in the summer to Antarctica in the winter, and you have to have the same instrument operate over all those temperatures. That's probably one of the biggest challenges. Plus, you put it on top of a rocket and you shake it around, and then you throw it down onto Mars and you bang on the surface, and all that has to be really, really light because you can't take very much mass. So those are really the biggest challenges. I mean, it's easy to measure less than an atom in a laboratory, but like I said, doing it in the dirt on Mars after you've shaken it and put it down, that's the tough thing. And then Gary PN1 asks, will SEIS be turned on when HP3 starts hammering? If so, do you expect to see anything? See my answer 5 minutes ago. And ST West asks, could you expand on the underlying mechanism behind the faults observed on Mars? So yeah, that's actually kind of interesting because again, all those faults are being driven by the heat engine. So how does this heat engine actually drive these things? Well, if you have a planet that starts off hot and it gets colder and colder, it shrinks, right? As you get something colder, it contracts thermally. As it contracts, different materials contract by different amounts, and the surface contracts at a different rate than the interior. And so you put the crust into either compression or contraction, depending on the details of how things are built. And so you can get it to be buckling as it gets kind of trying to squeeze onto a smaller and smaller ball underneath, or you can get it to actually be pulling apart and cracking if it's actually contracting faster than the interior. So it's really this kind of contraction of the planet that we think is mostly what's behind the faults that we see on Mars. There's other things that cause the faults when you make a big volcanic plateau like the Tharsis Plateau on Mars, which has volcanoes that rise up 25 or 28 kilometers above the average elevation. Those create big stresses, and as they try to relax, they cause cracking as well. And so those are some of the things that can cause Mars quakes. Have a question from inside here?
Yeah, hi.
Hi.
Sort of a follow-up to the nuke Mars question. Are there any steps being taken to map any potential meteor impacts on Mars so that like a mass could be imaged beforehand to help you gather relevant data if something big actually hits there and resonate,
Yeah, I mean,
similar to what you were talking about, like actually launching something to hit it, like.
So you're asking, are we actually putting together a database so that we can look in the future at
yeah, so if something's
meteorite
going to impact, you can try and measure the mass of that object and then get more
yeah,
relevant data from it.
That is going on now, again, with Mars Reconnaissance Orbiter. It has two different cameras. It has sort of what they call the Ctx camera, which is kind of medium resolution, which used to be really high resolution, but it's at the kind of tens of meter kind of resolution, and it can see those black blotches. When a meteorite hits Mars, what it does is it kind of blows the dust off, and that makes that contrast. And then when they see one of those, they go back with their high resolution camera and actually look at it at less than a meter resolution to be able to see the impacts. So CTX is already I think CTX has already covered the entire planet once with that medium resolution. So we already have kind of a base data set to use. And as long as we have an orbiter in place to take further images, we'll be finding more and more of these meteorites. One of the things that we hope to do with InSight is actually to constrain the rate of impacts a little bit better. Because with the cameras, it always sees it. If it's relatively featureless, has dust, so there's lots of places where they can't see. If that map I put up there, it has some places that had lots of impacts and some places that didn't have any, and that's not because they didn't hit there, that's just because it's hard to see them. With a seismometer, we'll be able to see anything over a certain size at a given distance, and so we should be able to put a better constraint on the rate of meteorite impacts on Mars today.
Thanks.
Sure. So if there's no more questions, I guess I'll just say good night. And if you want to come up and talk to me for a little while, I'll hang around for a while. There might actually be